Okay, good evening. Welcome to Pavitra classes. Next topic in the pharmaceutical analysis is infrared spectroscopy, IR. It is very important in the pharmaceutical analysis. IR is very important topic. IR, NMR or mass are the very important topics in the pharmaceutical analysis. So we will study what is IR, how it is interpreted, what are the instrumentation part of the IR, and what is the principle of the IR today. Infrared spectroscopy or vibrational spectroscopy. It is also called as the vibrational spectroscopy or infrared spectroscopy, concerned with the infrared radiations which result in the vibrational transitions. So it is seen as it will collect the vibration of the molecule. It is for that purpose it is also called as the vibrational spectroscopy. IR spectra is mainly used in the structural elucidation. So mainly if unknown compound is there, or if unknown compound is there, by the structure elucidation, by the functional group elucidation, structure elucidation can be done, naming can be done, then the compound can be identified. So what is the principle behind the IR? So atoms or groups of atoms connected with the bonds. As we know in organic chemistry, all the atoms will be connected in the bonds in the molecule. The bonds are analogs to the springs and it is not rigid by the nature. So the bond between the if it methane molecule is there, bond between the carbon and the hydrogen. So it is not rigid. It has some vibrations. It will be moving like a spring. How the spring will be moving closer and farther, like that the spring motion, continuous motion will be there in the organic chemistry molecule. So this is called as the natural frequency of the vibration. So inside that molecule the bond will be having, it is not in the rigid nature, it will having the spring motions, spring continuous motions. That motion will be called as the natural frequency of the vibration. When the infrared radiation will be fall on that particular molecule, whenever that natural frequency of vibration is equal to the applied infrared frequency, the peak can be observed of that molecule. For that vibration frequency will be particular for the particular bond of the molecule, like with the functional group, if alcohol is there, ether is there, carboxylic acids are there, like that they will have the exact vibrational frequency for that. Then they can be for that unique frequency we can identify the functional group present in that material. So by that, whenever that applied infrared frequency is equal to the natural frequency of the vibration of the bonds, then the IR peak will be generated. So IR spectroscopic processes, the quantum mechanical energy levels observed in IR spectroscopy will be, I told, molecular vibrations. So natural molecular vibrations will be there, that will give the IR peaks. We perceive this vibration as a heat. When we say covalent bond between the two atoms is often a certain length, then average because of the bond behaves where vibration of the spring connecting to the atoms. So the spring molecule. So this you can see the picture here like this. If it is a molecule, the bond between this will be like this yellow bond. You can see here it is the moving picture, spring like it will be moving closer and moving farther. This is the natural frequency of the vibration of the diatomic molecules. So this is the oscillating like a spring. It has a continuous oscillation movement. So whenever this movement is equal to the applied infrared frequency, then the IR peak can be generated. This is the natural frequency of the molecule. So every bond or a portion of a molecule or functional group requires different frequencies of for absorption. So it gives the for a particular bond or particular groups, it has a unique range for that frequency. For the uniqueness, we will get the functional group. We can identify in the unknown compound the functional group, and character peak can be observed for each functional group present in the molecule. So in pharmaceutical analysis, so many electromagnetic radiation are there. After the UV, infrared radiation will take place, that is the mid IR. So in the IR, three regions are there. One is the middle infrared range, near infrared range and the far infrared range. Usually in the pharmaceutical analysis, mid IR range is used at a wavelength of 25 microns to 2.5 microns, and in the wave number of 400 centimeter inverse to the 4000 centimeter inverse. So in other region, near IR and far IR, it is not used in the pharmacy field. In the pharmacy field, only mid IR is used. So you can see the picture. This is the electromagnetic radiation. So after the ultraviolet UV, and this is the visible radiation UV and visible, then infrared range comes. In this wavelength in microns, you can see near IR, mid IR and the far IR. So this mid IR range is used in the pharmacy analysis or pharmaceutical product analysis. So next is the criteria for a compound to absorb the IR radiation. So change in the dipole moment. So whenever the molecule has the dipole moment by the natural frequency of the vibration, once the IR frequency is generated on that molecule, change in the dipole moment gives the IR peak. And also it is very important that applied IR frequency should be equal to the natural frequency of the vibration. Otherwise the compound will not give the IR peak. Whenever that equals IR frequency, applied IR frequency equals the natural frequency of vibration of the molecule, then only it gives the IR peak. So in the vibrations, so after the vibrations, so many types of the vibration are there in the IR. Majorly two types, stretching vibration and the bending vibration. So stretching vibration, in the stretching vibration usually bond length will be occurred, as the name stretch. Stretch means bond length. It will take far and it will take near. So bond length of the bond will be altered. In the bending vibration, bond angle will be it will be bent. So bond angle will be altered. In the stretching, again two subclasses are there. One is the symmetrical stretching and asymmetrical stretching. In the symmetrical stretching, bond length usually increases and decreases symmetrically. If two bonds are there separated, the bond length of the two bonds will be increases and decreases symmetrically. At a time, two bonds will be, length will be increased and decreased. That is called as the symmetrical stretching. Second one is the asymmetrical stretching, in which bond length, one bond will be, length will be increases, and in other bond it will be decreases. Next is bending vibration. As I told, it has the changing in the bond angle. Bond angle change will be altered. Bond angle will be altered in the bending vibrations. In this, in plane bending is there, out of plane bending is there classes. In that, in plane bending subclasses two are there. One is the scissoring and one is the rocking. In the out of plane bending, two are there. One is the wagging and one is the twisting. So in plane bending, scissoring, bond angle will be decreased. As the scissor we use in the home, scissors will be used. Whenever you are cutting with the scissors, scissor will come closer. So bond angle will be decreased here. In the rocking, bond angle will be maintained, but the bond will be moving with the same plane. So whatever, if the 40-degree angle is there, that will be maintained in the rocking. In the out of plane bending, twisting and wagging will be there. So in which both atoms move in the one side in the wagging, and twisting, one in the plane, one in the above plane and one in the below plane. So you can see this 3D structure of all the vibrations. So these are the stretching, oscillating in the bond length, that is the stretching. So both, this is the asymmetric, symmetric stretching, both will be increasing at a time and both will be decreasing at a time. This is asymmetric, one will be increasing and one will be decreasing. You can see this 3D pictures. In the bending vibrations, scissor, this is having the in plane bending. In plane bending, this is scissoring. You can see in this 3D picture, it moves like a scissors. This is scissoring. This is rocking. Bond length will be maintained and it is taking. In twisting and bending, wagging, this is wagging, and in one plane, if it is wagging, one bond is, both are in one plane, then it is wagging. Twisting means one in the above plane and one in the below plane. You can see, identify the molecule with this 3D movements. Like this, bonding vibrations will be taking place. This is stretching in the symmetric stretching, and this is asymmetric stretching. This is scissoring, bending, in plane bending, rocking, in plane bending, out of plane, twisting and wagging. Next is the infrared group analysis. So in the primary use of the IR is the detection of the functional group. Whenever unknown pharmaceutical compound is there, if you have formulated any unknown compound, once the synthesis is done, you have to check the first you have to identify what compound is formulated in the laboratory. For that, first you are identifying the structure and functional group of the compound. Once the functional group you got, you can draw the structure, you can name that product. So for the detection of the functional group, IR is used, because IR looks at the interaction of the electromagnetic spectrum with the actual bonds. It provides unique quality probe functionally of a group molecule. As a functional group are merely different complication in the different bonds. So for the single bond, double bond, other functional groups, it has a unique characteristic peak. So by that, functional group can be identified. Since most of the type of the bonds, especially covalent bonds, covalent molecules have the same energy, like carbon-carbon double bond, carbon-double bond, oxygen, carbon-hydrogen single bond, nitrogen-hydrogen bonds, they show up the similar regions for the IR spectrum sometimes. But if it is attached to the other atoms, electronegative atoms like that, then uniqueness of the characteristic peak can be regenerated. Remember, all organic functional group are made up of the multiple bonds. They show the multiple IR band peaks. So you can see like this, you will get the, in this is the IR peak of the compound, you can see here. So the four primary regions of the IR are there. So one is the bond to hydrogen, triple bonds, double bonds, and the single bonds. So bonds to hydrogen, OH, NH, CH. These bonds, oxygen hydrogen bond, nitrogen hydrogen bond, and the carbon hydrogen bond. This graph is taken place in the 4000 centimeter inverse to 2700 centimeter inverse. This is bonds to OH range, triple bond range, carbon-carbon triple bond, and carbon nitrogen triple bond, usually 2700 centimeter inverse to 2000 centimeter inverse. Double bonds, carbon oxygen, that is carbonyl bonds, nitrile bonds, carbon and nitrate nitrogen bond, carbon-carbon double bond, usually 2000 centimeter inverse to 1600 centimeter inverse. Then 1600 centimeter inverse to 600 or 400 centimeter inverse. This is called as the major fingerprint region. This region is called as the fingerprint region. Carbon-carbon single bond, carbon-nitrogen single bond, and the carbon-oxygen single bond can be seen in the graph here. So these are the four major regions in the IR spectrum: bonds to H, triple bonds, double bonds, and the single bonds. This is about the infrared group analysis general introduction. So generally the four major classes are there in the interpretation of the IR graph. Next, coming to the infrared instrumentation. So in the instrumentation source, it is there, sampling techniques are there, then detectors are there, monochromators are there, then detectors are there, then the signal readings specially done in the computer. So source, almost all radiation source split into two beams. Usually in the IR source, radiation source will be split into two beams, because half passing to the sample, another half passes to the reference area. So whenever in the compound analysis, you have to keep one reference compound and the sample compound to match the graph, and with the rotating mirror and the light interrupter. So we need in the both cells, sample cell as the reference cell, we need the radiation. For that, in between that, rotating mirror will be kept, or light interpreter will be kept. So half of the source light and the half of the source light will be fall into the sample cell, and half will be fall into the reference cell with the rotating mirror and the interrupter. So what are the ideal source requirements? So what are the qualities of the IR source? To check that, it should be continuous over the wavelength range used. So whatever we are using in the mid IR range, 400 to 4000 centimeter inverse, in that it should be in that range, that light source we should be continuous. It should cover wide wavelength range. It should be constant over the period of the time. These are the major ideal characters or ideal necessary characters of the IR radiation. Majorly used lights are nurse glower, globar sources and the heated wires. These are the lights used for the source of the radiation. Apart from this, laser source also used UV. All of these heated sources emit continuous radiation with a spectral output very similar to that of the black body radiation sources. So one by one we will study nurse glower. So this is the nurse glower rod. Typically it was in the form of the cylindrical rod. Now it is not used. It was old technique. Cylindrical rod, tube having the diameter of 1 to 2 millimeter, length of 20 millimeter, sealed by the platinum leads ends to permit electrical connection. So it is composed of a mixture of earth oxide like zirconium oxide, yttrium oxide, erbium oxide, and in the ratio of 90:7:3 by weight. They operated by being heated around 2000 degrees Celsius. Initially they required external heating. So why it is not used now? Because it has to keep for heating for early stage only. After that the compound it is done. So preheating is required for this product. So it should reach the around 2000 degrees Celsius. Initially they required external heating because material is the insulator at a room temperature. So now nurse glower are fragile. They have large negative temperature coefficient of the electrical resistance. So it should be preheating is necessary for this. So it takes a too long time for the preheating. Then after reaching that temperature you can kept for the sample analysis. So it is not used because of this reason only. It needs the preheating. Resistance decreases with the increasing temperature. The source circuit must be designed to limit the current, prevent the rapid heating and the destroyment. So in that temperature destroys the rod also. Because of that the nurse glowers are not used. Next is the globar sources. Globar is a rod of the silicon carbide. It is this picture you can see. This is the silicon carbide rod. Around the diameter is 5 millimeter diameter, 50 mm long, which is electrically heated about 1500 Kelvin. Compared to nurse glower rod, nurse glower source, it is less temperature, but it has also a high temperature only. Water cooling of the electrical contact is needed to prevent the arcing. So the rod will create the arcing when it is reached to that temperature. Then water cooling is needed. No preheating necessary. Directly you can put in this. Spectral output is comparable with the nurse glower except at short wavelength. So the globar source does not give at the short wavelengths. The signal cannot be generated. This is the disadvantage of the nurse glower, and the output becomes the larger. Next is the incandescent wire source. So this is also one of the source of the IR. Lower intensity IR source, but longer life than the globar and the nurse glower, because after in the first it will destroy the rod due to temperature. Second one, water arcing will be done. Water cooling is necessary. In this it is the life of this wire source is more, but tightly wound spiral nichrome wire heated to 1100 Kelvin by an electrical current. Similar source of the rhodium wire also used for the ceramic cylinders. These sources are longer lasting but lower intensity than the glower, nurse glower and the globar source. Its intensity is less compared to the previous two sources. Next is the mercury arc lamp. This is the mercury arc lamp used for the usually far IR region. So it is pharmaceutically not used. This source is also not used in the pharmacy. It is a high pressure mercury arc which consists quartz jacketed tube containing the mercury vapor at the pressure of the less than the 1 atmosphere. When current passes through the lamp, mercury is vaporized, excited, ionized, then it will give the plasma discharge at the pressure. So when it takes the heat, mercury will be vaporized, excited, it gives the light source. In the UV visible region, in the UV visible spectroscopy also, the mercury arc lamp is used as a light source. It emits the mercury emission lines and are very narrow, discrete, but emits in the intense continuum in the only far IR region, as I told earlier. Next source is the tungsten filament lamp. Ordinary tungsten filament lamp, quartz halogen lamps, this is the picture of that, contains a tungsten wire filament, iodine vapor sealed in a quartz envelope bulb, used for near range of the IR region. So this is also in the not in the mid IR range. So in a standard tungsten filament lamp, the tungsten evaporates from the filament and deposits the lamp wall. This is the principle of that. Usually it takes the heat and it evaporates the filament, deposit on the lamp wall, and it gives the source. This process reduces the light output as the result of black deposit. So tungsten, when it is deposited, it gives the black deposited on that wall, then it gives the light output very less. So it is very rarely. So this is the disadvantage of the tungsten filament lamp. Halogen gas in a tungsten halogen lamp removes the evaporated tungsten and the red deposits of the filaments, increasing the light output and the source stability. This is about the sample source of the IR spectroscopy. These are rarely used sources now, but now UV rays as laser sources are used as a source of the IR spectroscopy. Next is the sample handling technique. So sample handling technique is very important in the IR. So it has two sample handling. One is the solid sample handling. It may be the powders, crystals, like that. Second one is the liquid sample handling. Usually for solid samples, pressed pellet technique is used. So pressed pellet technique is usually mixed with the KBr, that is the potassium bromide, and compressed into a thin transparent pellet using the hydraulic press and used for the analysis of the others. So how it is done? Around 1:500, like that ratio it is taken. So with the pestle motor help, the solid samples and KBr is mixed with the hydraulic press, and it is taken as a smooth particles. So once with the hydraulic press, with the pestle motor it is mixed, then the sample is mixed with the KBr powder, then it can be added in the analysis. So this is the sample handling. Other than that, KBr, Nujol and Nujol Mull techniques are used, especially in the Nujol Mull liquids. For liquids, sample can be held with the liquid sample cell, usually with the alkali halides. Organic solvents are also used for the mixing of the liquid, that is especially chloroform. Third part of the IR source is monochromators. Once the source and the sample handling is done, the monochromators are used for the converting of the multiple wavelength of the multiple beam of the light to single wavelength. Filters are made up of lithium fluoride are used, or prism made up of potassium bromide, cesium iodide, sodium chloride, thallium bromoiodide are used. Diffraction gratings are used, made up of the alkali halides are also used as a monochromators. Next is the detectors. So detectors are used for to measure the intensity of the absorbed infrared radiation. So once the sample is kept in the sample cell, some of the light source is absorbed by the sample in the sample cell, but the unabsorbed, whatever the radiation is there, that will be fall on the detector. To measure that intensity of unabsorbed infrared radiations will be used for the detectors. Usually thermocouples, Gole cells, bolometers, thermistors and pyroelectric detectors are majorly used. So the detectors can be taken into three classes. One is the thermal detectors, pyroelectric detectors and the photoconducting detectors. So we will study one by one. One is the thermal detector. Usually their response is depending upon the heating effect of the radiation. So how much heating is taken place? Thermal means heat. So how much heat is there? That can be identified with the thermal detectors. It can be used over the wide range of the wavelengths upon the wave rate to operate in the room temperature. With these devices, small black body resultant temperature rise is also can be measured. So power level is very small for this. Heat capacity of absorbent element be small because under the best conditions, usually in the few thousand Kelvin. Size and thickness is made up to the small and connect into the IR beam of the surface. So the intensity will be less. Next is the major disadvantages of the thermal detectors. So thermal noise from the surrounding can be done. So heat, slow response time, it takes much time, and lower sensitivity. I told lower sensitivity related to the other type of the detectors. So minimizing the thermal noise. Thermal transducer, sometimes it is used in a housed in a vacuum, carefully shielded in the external thermal radiation. So it may give the external thermal radiations also outside the lab also. So because of that, it is very rarely used. The beam from the source also is chopped. In the first type of the thermal detector, thermocouples. So thermocouple consists of a pair of junction of different metals. For example, two pieces of the bismuth fused to either end of a piece of the antimony. So usually bismuth and the either piece of the antimony, two pieces metals are used in the thermocouple. The potential difference between the junctions. So it acts in the electrodes. Voltage between the junction changes according to the difference in the temperature. So once the temperature is taken place, bismuth and antimony, it gives the radiations or electrodes can give the ions in the junctions. So the transducer junction for IR radiation junction is usually blackened to the improve its heat, because color black absorbs the heat, absorbing capacity, and sealed in an evacuated chamber with a window that is transparent to the IR radiation. Reference junction. So in these two junctions will be there. One is the transducer junction, one is the reference junction. So in the house, in the same chamber, it will be shielded with the incident radiation. So temperature response in case of a well designed thermocouple, temperature different will be 10 raised to minus 6 Kelvin. This is the outline of the thermocouple detector. So you can see here thermocouple junction will be there, reference junction will be there. So spectrometer slit, this is the radiation slit for the sample and this cell. So junctions, it will take the reading. The reference junction, again it will take the reading. Due to the amplifier, it gives the negative feedback, and to amplifier, it gives the with the current falls on the amplifier, it gives the result. Next is the thermopile. Piling means pooling of that. Pile means to enhance the sensitivity of the thermocouples, connected series of the thermopiles. So the series of the thermocouple receptors gives the thermopiling. It means two junctions will be thermocouple, two junction will be joined. So with the black body, because black take the heat. This is the black body, this is the thermo element 1, this is thermo element 2, this is cold junction, this is hot junction, this is the diaphragm. In between joining region is called as the diaphragm. This is the thermophile cross sectional sketch. So by the heat from one range, this is the hot junction, from this to this heat is generated. Because of that, this is hot junction, this is cold junction. The heat is moving from this place to this place. So thermocouples connect with the series of the thermopiles. So one unit is called as the thermophile. A series unit of the thermophile is there, that is called as the thermocouples, or two more are there, that is called as the thermocouples. Next detector is the bolometer. It is used in the far IR detector. Bolometer, changing resistance when it is heated. It is constructed of strip of metals such as platinum, germanium and the nickel of the semiconductance. So it has the semiconductance character. Relatively charged change in the resistance as a function of temperature is resulted. So large response time is there. So it should take the temperature, then it should fall the reading. It takes the large response time. You have to wait very long for the response of the time. Rarely it is used in the mid IR, other IR transducers. IR range usually for germanium bolometer, it is 5 to 400 inverse. So centimeter inverse. That is, it is used in the especially other IR region, not in the mid IR region. Next is the pyroelectric detectors. These are the pyroelectric detectors. It consists of the pyroelectric materials, insulators, dielectric materials, special thermal and the electrical properties. So in between previous whatever bolometer, thermopile, thermocouples, thermal detectors, this is responsible for the heat, only heat. In this pyroelectric, thermal properties, also electric properties are taken place. So for that it is combining of the pyroelectric, thermal and electrical properties. Triglycine sulfate, It is usually deuterated or with a fraction of glycines replaced by the alanine. Is the most common material is used in the pyroelectric infrared detectors. This is the formula of the triglycine sulfate. Unlike the other thermal detectors, the pyroelectric effects depend on the rate of change of this detector temperature rather than the temperature itself. So here rate of change also measured and also temperature. I told this is thermal property also and the electrical property also. Third type is the photoconducting detectors. So these are the most sensitive detectors. They are very used. They rely on interaction between the photons and the semiconductor. So it is not only semiconductor, it gives the reaction on the falling of the photons. The detector consists of thin film of semiconductor materials, lead sulfide, mercury cadmium telluride, indium antimonide deposited on the monoconducting glass surface and sealed into evacuated envelope to protect the semiconductor from the atmosphere. When IR source is absorbed, non-conducting valence of the electric promotes the higher energy to the conducting state. So the movement of the conductance is taken place. The voltage drop is a measure of the power of the beam radiation. So voltage will be dropped. The lead sulfide detector is used in the near IR region, and mid and far IR region mercury cadmium tellurium detector is used. So for pharmaceutical use, mercury cadmium telluride is used. It must be cooled with the temperature of the liquid nitrogen 77 Kelvin to minimize the disturbance. So it is cooled outside with the mercury liquid nitrogen. So this is the comparison: thermocouple, bolometer, pyroelectric and the photoconducting. Photoconducting are very used detector in the IR. Thermocouple, thermoelectric effect, dissimilar metal junctions. So it is very cheap, slow and insensitive. Bolometer, it has nickel, platinum resistance thermometer at 1.5 K, highly sensitive in the 400, more than 400 centimeter inverse. Pyroelectric, triglycine sulfide, piezoelectric material, fast and sensitive in the mid IR. Photoconducting, it is very fast and sensitive. Lead sulfide, mercury cadmium tellurium light sensitive resistance thermometer at 77 Kelvin. It is cooled in the liquid nitrogen. This is very fast and sensitive detector, photoconducting detector. Last part is the recorder and the plotters. So they are used in the record the IR spectrum. Especially computers are used with the IR machine. Type of the instruments. So in the IR instruments, single beam IR spectrophotometer are there, double beam IR spectrophotometer are there, newly FTIR machine are there, Fourier transform infrared spectrophotometers with advanced feature like matching the spectra identification. It has the already feeded data in that. Matching spectra, you can done the unknown compound, you can match the spectra of the unknown compound with the known characteristic peaks. Identification of the functional group using the library databases. FTIR machine has the library database, so it has the library for the particular regions. So you can, software also available in the FTIR. So you can match very easily with the FTIR machine. It is very advanced machine, FTIR, Fourier transform infrared spectrophotometer. So the advantage over the FTIR over the dispersive instrument. So dispersive are the single beam IR spectrophotometer and the double beam IR spectrophotometer. These are the dispersive instrument. Whereas FTIR is the sophisticated with having the library databases and the softwares. It is the rapid, more sensitive, accurate, and you can have the computational capabilities. You can compare the graph. So the time will be very less and you can do the work more in that time with the FTIR machine. So this is the schematic representation of the dispersive IR meter, not Fourier. This is the dispersive meter. So you can see here, this is the yellow circle is the IR source. The light is split into two with the rotating mirrors. So these are the rotating mirrors or light slit. So this is the sample cell, this is the reference cell. To get in the both line light, it is slitted. So this red line is light passing, then lights plastered, again rotating mirror will be there. Chopper, after the chopper, monochromators, the double lights will be converted to single monochromator light. Then the detector IR detector, it is fall on the this grating. This is the monochromator gratings, diffraction grating. Then it falls on the detector, and you can then the record analyzer. So this is the schematic representation of the IR spectrum. Next is what is FTIR? A spectrophotometer is an optical instrument used to measure the properties light over the specific portion of the electromagnetic spectrum. So in a very less range, 5 microns, 20 microns, like that, in the FTIR spectrometer you can get the very low range also. So Fourier transform infrared spectrometer is obtained an infrared spectrum by first collecting an interferogram of a sample signal using interferometer. So in this, interferometers are there. In the dispersive machine, interferometers will not be there. So it is very useful for the interferometer is instrument used for the superimposing of the images. So two or more images waves superimposing to detect the difference between the FTIR and the Michelson interferometer. So Fourier transforms defines a relationship between the signal's time domain and its presentation of the frequency. So once you keep the one sample, it will give in this time this sample can be analyzed. So that also it will give in with the Fourier transform machine. So it gives the both relationship between the signal and the time domain. The data will not be lost in the Fourier transform machine. Fourier transform of a signal continuous complex valued signal capable of the valued complex for the complex molecule also it gives the continuous signals. So FTIR theory, it is usually Bowman MB 100 FTIR describes here modern. The heart of the FTIR is usually Michelson interferometer. The mirror moves at a fixed rate, so it has very automatic features. Its position is determined very accurately by counting the interference fringes of a collected helium neon laser. The Michelson's interferometer splits the beam radiation into two parts, same for the sample cell and the reference cell at different lengths, and recombine them with the monochromator. A detector measures the intensity variation of the exit beam also and the path differences. So the monochromatic source simples in wave intensity direct detector due to the constructive and the destructive interference can be seen. In general case, usually wavelength of the spectrometer detectors indicators the wavelength added together. So idealized light source interferogram are also theoretically can be produced. So then it is when the retardation is 0 with the formula OM is equal to OF plus D. So radiation source retardation with the figure 1 and 2, when the retardation is 0, detector sees maximum because all wave numbers of the radiation add constructively. When retardation is half, the detector sees minimum wavelength at 1. So all wave numbers can be intensified. So 0 retardation can be also checked, half can also checked. So this is the figure 1. So this is the moving mirror, the IR band source, KBR beam splitter, and the measure interference. So retardation is equal to 2 into OM into OF. So by the integration of this ice cloud of this transmittance can also taken place. So cloud and in cloud. So these are the formulas for the FTIR basics. This is the Michelson's interferometer. It is used for the detector purpose. So moving mirror, fixed mirror. So one mirror will be moving here, one will be fixed to get the exact wavelength. Beam collimator are used. Then source. So fixed mirror, then it is again splitter with the beam splitter. Both sides fixed mirror and moving mirror. Then the light source will be with the collimator or the monochromator. The detector will be fall into place. So application of the FTIR is identification of the inorganic compounds, organic compounds, identification of the components of the unknown mixture, analysis of the solids, liquids and the gases in remote sensing, especially in the atmospheric spectra also it can measure the solar irradiance. So sun radiation also can be measured with the FTIR because it has the best library databases. You can compare the signals with the already feeded library data of the functional groups. Long wave terrestrial radiation spectra can also use. It can also used for the satellite checking. Used satellite checking on the probe of the spaces. Application of the IR, as I told earlier, it is usually for Measuring of the functional groups of the structure elucidation. So group frequency from 4000 to 1500 centimeter, fingerprint region 1500 centimeter inverse to 400 centimeter inverse, where the characteristic peaks of the functional group are also seen in this region. That's why it is called as the fingerprint region. Next is the identification of the unknown drug substances. Once the IR spectrum of the standard peak can be compared with the unknown compound for the identification purpose. Impurities in the samples can also be identified. Study of the hydrogen bonding can also done. Study of the polymers, cis-trans isomers can also studied. Qualitative analysis and quantitative analysis both can be done in the pure form impurities, and also comparison with the extinction peak of the sample and the standard can also done. This is also called as the baseline technique. Once the comparison between the sample and the reference cell, the extinction peak, if it is not there in that sample cell, extinction peak, the extra peak is seen in the standard, that is called as the baseline technique. This is about the application of the IR. So these are the characteristic IR absorption range. So you can see the for these bonds, this wavelength wave frequency range is there in the centimeter inverse. These are the functional groups. So you can see here 3640 centimeter inverse to 3610. Here S and S means what it is there. I have given here S means strong, SH means sharp. So strong sharp peak is observed for the OH stretching. OH stretching, H bonded, strong and broad. M means here, M means medium peak, NS narrow, strong, like that. All the bonds gives in this region. You can see here these regions for particular functional group. OH 3640 to 3610. Carbonyl group stretching, carboxylic acid stretching, ester stretching, like this. The ranges will be vary here in this stretch. Only carbonyl stretch. If it is carbonyl group, carboxylic acid group, ester group, aldehyde group, the ranges will vary in the slight variation. So by this characteristic range you can, and characteristic peak, you can get this. Only specially alkyne, this carbon-carbon triple bond, it gives the wide peak. W means it is wide peak. This gives again alkanes. This is the range. So you can see the ranges in this. Again around 1500 to 400. This is the fingerprint region 600 because of the single bonds 1500, like nitrogen oxygen asymmetric stretch nitro compounds, carbon-carbon stretch in ring, especially in the aromatic group. This range is seen. CH rocking alkanes, symmetric stretch, CN stretch, CO stretch in the alcohols, CH wag in the alkyl halides, especially in this range, and CH bending alkenes. These are called as the, because by this characteristic peak you can identify the structure of that compound. Structure elucidation can be done. So this range is very important. CH aromatic, CCl stretch, carbon chloride stretch, alkyl halides 850 to 500, medium peak can be seen. CH rock alkanes 700 to 610 alkynes, like this. This range can be seen. These are the ranges for the particular bond and particular functional groups. So we will see one example. So this is the ethanol molecule CH3 CH2 OH. So you know this is the ethanol structure. Once the IR graph is plotted, percentage transmittance in the y-axis and the wave number in the x-axis. This is the stretching. So OH, this OH functional group stretching, it is 3230 to 3500 centimeter. This broad peak, like this you can see here. This is OH peak, you can see in the group OH stretch. So this is ethanol is the alcohol, OH stretch 3640 to 3610. So you can see here it is in that range only, 3500. Some, if it is some impurities, you can see this range also variation. In this is the OH stretch, this is CH stretch. So this CH stretch 2950 to 2850. This is the narrow sharp bond. Then it is the CO stretching. Carbonyl CO is only usually seen in the, this is fingerprint region. This is bonds to H. First, I have in general interpretation I have given this. This is CO stretching. You can see here. By this you can see that CH stretchings are there. How many peaks are there? By counting that CH, how many molecules are there? You can count OH stretching and CO stretching. Then you can interpret the structure. Another one. This is the benzoic acid structure. This is the graph of the IR. Then interpreted spectrum from the benzoic acid KBr disc. OH vibration, stretching vibration, you can see here. This is overlapped because of the KBr. Aryl CH stretching vibrations, you can see here. This is aryl CH stretching because it is aromatic CH stretching vibrations. So you can see the numbers also, peak number also through the stretching. C double bond O stretching vibration.